Space looks calm, almost empty even. But that's just how it appears on the surface. In reality, space is constantly active. Everything is moving. Our entire solar system is traveling through the Milky Way galaxy at around 800,000 kilometers per hour. And that's only one layer of motion. Because while stars, planets, and systems are all moving, they're also interacting through one invisible force: gravity. And gravity is where things start to get interesting. Now, most people imagine planets as stable objects, locked into perfect orbits around their stars. And for the most part, that's true. But not all planets stay where they were formed. Some get thrown out completely. These are called rogue planets, planets that no longer orbit a star. They drift through interstellar space on their own. And based on current astronomical models, there could be billions of them in our galaxy. They are not rare accidents. They are actually a normal outcome of how planetary systems form. Here's how it happens. In a young solar system, everything is chaotic. Planets are forming, colliding, and shifting orbits. Gravity is constantly pulling things in different directions. And sometimes, one planet gets too much energy from these interactions. So instead of settling into orbit, it gets ejected entirely, flung out of the system. And once that happens, it doesn't stop. It just keeps drifting, forever. Now here's where the real question begins. What would happen if a rogue planet entered our solar system? Not crashing into anything, just passing through. To understand that, we need to understand something first. Our system is not stable in the absolute sense. It's only stable because nothing has disrupted it recently. Earth's orbit exists in a very specific balance. The Sun pulls Earth inward with gravity. Earth moves forward through space at high speed. That balance creates a stable orbit. And that orbit is the reason life works. Because distance from the Sun controls everything: temperature, weather, oceans, even long-term climate cycles. So now imagine something massive enters the system. A planet the size of Neptune or Jupiter. It doesn't hit Earth. It doesn't need to. It just passes nearby. At first, nothing obvious happens. No explosions, no sudden changes. But gravity doesn't work like impact. It works slowly, over distance. And over time, even a small gravitational influence starts to matter. Earth's orbit can begin to shift. Not dramatically at first, just slightly more stretched. More elliptical instead of nearly circular. That small change has consequences, because it means Earth is no longer receiving consistent energy from the Sun. Some parts of the orbit bring us slightly farther away, others slightly closer. And that difference starts to build into real climate effects. Winters begin lasting longer. Summers become less intense. At first, it might look like natural climate variation. But it doesn't stabilize. It continues shifting. Oceans start responding slowly. Water temperatures change. And that affects ocean currents, which regulate global climate. If those currents weaken or shift, weather patterns across entire continents begin to change. And this is where the system becomes interconnected. Because climate is not isolated. It affects ecosystems, agriculture, water cycles, species survival. It doesn't collapse instantly. It breaks in layers. Some species adapt, others disappear. Food chains begin to restructure over time. Now here's something most people don't think about. Even sunlight itself would feel different. Not because the sun changes, but because Earth's distance from it changes. That means slightly less energy reaches the surface during parts of the orbit, which affects plant growth, rainfall patterns, and long-term atmospheric balance. But the effects don't stop with Earth. A passing planet also disturbs everything else in the system. Asteroids, comets, debris fields. Their orbits can be subtly altered. Some get pushed outward, others get redirected inward. Not immediately dangerous, but over long time periods, the probability of impact events increases. Not suddenly, gradually. And this is important to understand. This is not theoretical fiction. Rogue planets have already been detected indirectly. Using infrared observations and gravitational analysis, astronomers have found evidence of large, cold objects drifting through space without stars.
Instruments like the James Webb Space Telescope are now helping researchers better understand these objects. And planetary formation models strongly support their existence. Because systems don't form cleanly, they form violently, and gravity always produces leftovers. So the next question is, would Earth survive something like this? The answer is not simple, but it is not instant destruction. This would not be a sudden extinction event. It would be a long-term transformation. Over decades, centuries, or
Some parts of life would remain stable. Deep ocean ecosystems are extremely resilient. They don't depend on sunlight in the same way surface life does. Subsurface microbial life could also continue largely unaffected. Even humans, with enough technology, could survive in controlled environments. Artificial habitats, climate-regulated systems, closed-loop ecosystems. But surface Earth, the world we know today, would not remain the same. It would slowly shift into something unfamiliar. Not because of a single catastrophic moment, but because of many small changes stacking over time. And when you zoom out far enough, this becomes the bigger lesson. Our solar system feels stable because we experience it on human timescales, but on cosmic timescales, nothing is truly fixed. Stars move, planets drift, orbits evolve, systems interact. And stability is not a permanent condition. It's a temporary balance maintained by distance, mass, and timing. So when we look at Earth today, what we're really seeing is not a guaranteed safe system. We're seeing a moment of equilibrium in a universe that is always